Okay, let me walk you through practice problem 6 right here. Practice problem 6 is another gas stoichiometry problem. This one is kind of the opposite of the last one we did though. In this case, we're talking about water. When we run an electrical current through water, which sounds like a brilliant idea, doesn't it? Well, there's actually a process called electrolysis where you can do this safely and cause the water to decompose, so to break apart, into hydrogen and oxygen gas. The chemical equation is given right here for that process. What we want to know is what mass of water. So this is what we're trying to find. This would be a mass of water. That would be like our chemical B because that's what we're trying to find. How much of that do we have to decompose at 1.05 atm and 23.2 degrees Celsius in order to produce 3.6 liters of oxygen gas? Well, this oxygen gas, you'll notice, has a lot of numbers given about it. It has a pressure given right here. It has a temperature given right here, and it has a volume right here. All of those are values given for oxygen gas, which would be your chemical A. If I take a minute and look on the mole map, I can identify where I'm starting and where I'm going. So when I check out my mole map here, I see that I was given a pressure, volume, and temperature of a gas A, which was my oxygen gas here. So the values you're given is always going to be on the left side of this mole map because that's where you start at. What they're asking me to find is a mass of a different chemical, the water, a mass of B. In order to do this, I'm going to have to start this problem by using PV equals nRT, the ideal gas law. When I do that, I can solve for the N in that equation because the N, remember, would give me moles. So I'm going to start by using PV equals nRT. So to summarize here, I have this problem already worked out. I was given a pressure, volume, and temperature of oxygen gas, which would be like my substance A, and I'm asked to find a mass of water, which is my substance B. So I'm going to start by using the ideal gas law, PV equals nRT. To use this equation, I'm plugging in the numbers they gave me up above. So they gave me 1.05 atm, that goes right here. The volume they gave me was 3.6 liters, so I'm putting that in. Notice that N is what I'm solving for. N is my unknown here. R is a constant. It's always 0.0821. For my temperature, if you look here, you'll notice that I did something with my temperature before I plugged it in. And that is I added 273 to my value in order to convert it into Kelvin. If you're wondering about the sig figs, it's because this number, 273, was only significant to the ones place with no decimals. So my answer is only significant to the ones place with no decimals. So there are all my numbers, and now I have an algebra problem with one variable in there, that N. So let's solve for it. Right now, N is being multiplied by two other numbers, the 0.0821 and the 295 Kelvin. So in order to get N by itself, I'm going to divide both sides by those two numbers, the 0.0821, the value of R, and the 295 Kelvin, my temperature. When I do that division, I now have the N by itself on the right-hand side, which is good. And on the left, I have an expression. What I need to do now is enter that number in my calculator. When you enter that in your calculator, there's a couple ways you could do it, but I would start by putting 1.05 times 3.6 divided by, and then you'll want to use parentheses. If you put 0.0821 times 295 in the denominator, be sure and put parentheses around that. The other way would be to divide by each number individually. However you do your math, you get an answer of 0.16. The significant figures here, I'm limited to only 2 because that volume they gave me only had 2 sig figs. So I'm rounding it to 0.16. The units on this are moles. So if I look at the units over here, see how I had liters and atmospheres on top and liters and atmospheres in the numerator of that fraction, which was in the denominator. I also had Kelvin that canceled out. I was left with moles on the bottom of the bottom, so in the denominator of the denominator. That equates to being in the numerator, so my answer is in moles. Now, have I solved this problem? Not quite. Let's look on our mole. Right now, I am at moles of my chemical A. In order to get all the way over here to grams of B, the first thing I need to do is I need to make a mole ratio. So let's do a mole ratio. A mole ratio, remember, comes from the coefficients in your balanced chemical equation. When you do that, you get an answer for moles of B. So I'm going to do that in a stoichiometry calculation. For me, that's going to look like a times in a line problem. So for my stoichiometry part, I start with that number I just had, the 0.16 moles of oxygen, O2. Notice that was the chemical that they gave me the pressure, volume, and temperature for before. So when I used the PV equals nRT equation, the answer I got was for oxygen because those were all the values they'd given me. In my next step, because I started with moles of O2, I had to put moles of O2 in the denominator to make it cancel. In the numerator, I put the moles of what I was trying to find, my chemical B, which was water in this case. Now, where did those red numbers, those numbers in front come from? I almost gave away the answer. They came from the coefficients in the balanced chemical equation. If I scroll back up and look, I see that right here, the water had a 2 in front of it in the equation. The oxygen had no number, which is a 1. So in my mole ratio step here, I put a 2 as the numerator or the coefficient for the water, and a 1 is the coefficient for the oxygen. Now my next step, if I look at my mole map, is to convert from moles of B to grams of B. In order to do that conversion, I'm using a molar mass for the chemical B, which is my water. So in this particular problem, I'm going to put moles of H2O on the bottom because I need my moles of H2O to cancel out here. The moles of H2O gets a 1 in front of it because when you're using a molar mass, it's always for 1 mole. Molar mass is, by definition, the mass of 1 mole. Now I needed a molar mass, so you'll see that I added up the molar mass of H2O. So this is 2 hydrogens plus 1 oxygen added up to get a molar mass of 18.02. And then I did my math. That was my last step there. When I did my math, I got 5.8 grams of water is the answer. If you kept your answer for moles in your calculator and just used that answer rather than the rounded value here, you might have gotten 5.6 or 5.7. Those would all be okay here because we were using this 0.16, which was just the rounded version of the first number. So congratulations if you've done this problem. I think you're ready to go try some practice now. You'll notice your practice page doesn't have a whole lot of problems, but that's because a lot of them take a couple steps like this one. Good luck.